Welcome to our second clip on quantum mechanics, and we will continue to discuss the experiment that we have thought about in the previous clip, which was a two-slit experiment. Now, let's look again at what is actually seen in the experiment. As you can see in this video, which is a slow motion of a measurement, you see a measurement where each time we see one electron hitting the screen, and if we accumulate these electrons, we see the interference patterns. That was discussed in the previous clip. Now, basically, I would like to concentrate and single out a single incident seen in this measurement. Let's say that we are considering this experiment from the classical point of view. We have our two slits. We have our screen, and we release a photon, and what is seen in the experiment, in the measurement, we see a point where this particle, this electron, hit. Okay, so I'll call this stage where we observe this electron, and this is supposed to represent an eye, a measurement. We measure the position of the electron once it hits the screen. Okay, what can we measure? Let's say that it hits the screen at time t. We measure the position along the screen, and we measure the momentum. Now, if we know the forces acting on this electron during its trajectory, we can write down equations of motion. And work out what trajectory this electron took from its initial start. Say it was at position x0 and p0. And we can calculate this trajectory, which depends on the forces that were extracted on this particle. And basically, at any given point, we could point and say at time t1 it was here, at time t2 it was here. We can say even what was the momentum at each time. We know everything. Actually, if we measure x and p at the point where it hits the screen, we can perform time reversal and actually trace this electron back to its origin and know everything that we want to know about the trajectory that this electron took. Okay, that's the basic point of view of classical physics. Let's see what happens if we consider this experiment from the point of view of quantum mechanics. Okay, again, we'll start from our two-slit experiment. We have our screen. We see the electron hit at a given point, exactly as you have seen in the video we saw a few moments ago. We observe it, and that's our measurement. Okay, up to here, similar exactly to what we did in classical physics. Now, if we measure classical physics, we know x of t and p of t. First surprise that we have in quantum mechanics, we can't do it. We can actually say where the particle hit on the screen. We know nothing about the momentum. This is Heisenberg's uncertainty principle. And it's not that we're not clever enough to calculate it or to measure it. It's basically impossible to measure it. That's the first surprise that we have in quantum mechanics. Things that are accessible in classical physics can't be measured. Well, we could measure the momentum, then we would know nothing about the position. Okay, so what are we doing in quantum mechanics? It's important to understand that that quantum mechanics is basically a theory which describes probabilities. Meaning, we know nothing about x of t or p of t, but we know something about the probability of measuring them. Our knowledge is basically in the wave function, where the propagation in t, in some sense similar to the equation of motion, is in the Schrödinger equation. And what we extract from the wave function is basically the probability. What is the meaning of all this? Basically, instead of defining coordinates where this electron started, we will have a wave function that describes it at some initial time. How do we determine this wave function? We'll discuss at some later stage. From this wave function, we could, in principle, know the probability of where the electron was at time t0. The propagation in time is described by the propagation of the wave function, how it develops with time. And finally, at time t, we know the wave function at time t, and we could extract the probability of finding the wave function, of finding the electron anywhere on the screen. Could we tell you where this electron will land? Where will we measure it? The answer is no. The best that we can do is give you probabilities. And again, it's not because we're missing some ingredients of the system. In principle, that's all that we can give you. So we have a probability to see the electron at the screen at some position x, and that's actually our measurement. Now, the measurement does something very interesting. You may have heard about it as the collapse of the wave function. It's a very tricky and delicate point, and I'll expand on it in the next clip. Thank you.